Cecil Balmond is a Sri Lankan British engineer who is widely considered to be one of the most influential creators of his generation. He achieved advanced degrees in engineering from different universities, but went on to also become a renowned designer. He served as deputy chairman at Arup and led the acclaimed design group, the Advanced Geometry Unit. His design approach focuses on organizational systems, based on experimentation and research. Balmond has stated his aim to break down the separation between architecture and engineering, and this presentation explores the design process behind one of his most famous projects. The CCTV headquarters in Beijing is one of the most unusual skyscrapers in the world. As the name suggests, it was developed for the principal state-run broadcaster in China, but has been nicknamed the Big Shorts by locals. The building was designed by esteemed architect Rem Koolhaas in a joint effort between the OMA and Arup, adding to a long list of collaborations with Balmond. Forming a singular loop, it was envisioned as an expression of the interconnected activities within production. Comprising two leaning towers connected by right angles at the top and base, the building reaches a height of 234 meters. One of the key innovations for the building is its structural exoskeleton, which resembles an irregular grid. The pattern appears chaotic yet highly organized, a hallmark of Balmond's projects. It visually expresses the forces within the tube structure, as the mesh becomes finer in areas of a more concentrated load. The building may be described as a diagrid truss tube structure with interior columns. The diagrid frame contains multiple joint layers of alternating beam orientations. This essentially marries the columns, beams and bracings into one system for uninterrupted load transfer. As a result, the CCTV building has no movement joints and is one of the largest single structural systems in the world. To ensure that all elements act in unison, Balmond follows strong joint, weak member philosophy. As such, bracings are connected to the transfer trusses at singular pin joints only. To facilitate this, Balmond's team included innovative butterfly plate connections. These balance the loads from different directions and transfers them to the rest of the structure. Architectural form is a major driver, as the building was designed to be an iconic feature of the city's skyline. The aim was to make a statement representing a new era of Beijing architecture and inspire innovation among China's new high-rises. The team envisioned a looped structure that would allow free travel between all parts of production. Adequate floor space was also a requirement for the expansion of the state network. Located in a seismically active region, the headquarters is exposed to a high risk of earthquakes. It therefore must be able to distribute loads throughout the structure to resist lateral forces. The bracing pattern offers many alternative load paths. The issues of instability due to the form also required an innovative solution. The leaning towers and cantilevered overhang add extra complexity to the structure. Finally, the context of Beijing posed a challenge, as the building must be constructed and survive in a highly variable climate. Temperatures can vary by as much as 30 degrees Celsius between summer and winter. The total embodied carbon is approximately 295,000 tons of CO2 equivalent, which is a very high number, but not unusual for the building of this size. As expected, the steel within the structure has the largest contribution to the overall embodied carbon due to the high amount of energy required to produce it. One obvious way to reduce the carbon footprint of the structure is to use alternative materials with lower embodied carbons. For example, the concrete used in the foundations may be replaced with 50% ground granulated blast furnace slag. This would reduce the embodied carbon per unit from 138 kilos per ton to 89 kilos per ton. The diagrid pattern may be optimized even further to reduce the embodied carbon. Using modern design techniques such as finite element modeling to vary the angle and sizing of members rather than the grid density, the amount of steel in the diagrid may be reduced without sacrificing structural properties. The overhang at the top of the structure generates a lot of stress due to the cantilevering effects, so the diagrid at the base is dense to resist the bending moments. The embodied carbon of the building may be reduced by making the overhang lighter, for example by lowering the number of floors within it. The moment of the force can also be reduced by shortening the lever arm. Finally, tuned mass dampers or even innovative new seismic invisibility cloaks may be installed in the structure to reduce the effects of an earthquake. The existing building has been designed to be excessively stiff and strong to account for seismic loads, so the material usage can be reduced if these effects are accounted for. This is the updated carbon footprint with the suggested structural enhancements. Notably, the largest reduction in embodied carbon has come from the reduction in steel. The total embodied carbon has been reduced by 62,000 tons of carbon dioxide equivalent, which equates to a 21% reduction overall. However, the embodied carbon is still very high, and further actions may be taken to reduce it.